Hello and welcome to Guessing the Methods exam part 3. Now last year I guessed it, but this year it's my past students. They've got their own tutoring company. Now if you rate yourself as a mathematician, you should go to this link and apply for a job. Next year they're going to need more tutors to tutor students. Alright, let's get started. Alright, have a try and then I'm going to do it. Alright, here I go. So determine the gradient of a function. Now, big advice here, draw a picture. So, what have we got? Our function. I don't know what it looks like. It might look like this, might look like whatever. But what I'm trying to find is the gradient at x equals 1. That's the goal. What do I do? Find the derivative, let the derivative equal 1. So that's the function. It's very oddly written because it hasn't been simplified. So that's probably a first good job before we start deriving it to simplify it. Alright, so using our index laws, this is e to the 3 times x, so e to the 3x, times e to the x squared times e to the 5x. And then if you want to multiply things that have the same bases, you're just adding the powers together. So we're going to get e to the 3x plus x squared plus 5x. And we can simplify that to be e to the x squared plus 8x. Haven't really achieved anything yet. I've still got f of x equals, and there's my function. So I need the derivative of that. So f dash of x is equal to, now the derivative of an exponential function, we're going to bring that out the front, but the derivative of it. So 2x plus 8. And that's all being multiplied by e to the x squared plus 8x. The reason I emphasize all is because sometimes people leave those brackets off and they end up with 2x plus 8 times that. Okay, so that's important. What do I need to do now? We need to know the gradient at x equals 1. Alright, so we just sub in 1 for x. Alright, f dash 1 equals 2 times 1 plus 8. All of that is being multiplied by e to the 1 squared plus 8 times 1. Wow. Actually, not too bad. 2 plus 8 is 10. E to the, all of this, 9. 10e to the 9. Is that answer in our list? Yes, it is. The answer is A. Celebrate. And next question. Alright, nice easy one here. Have a crack at it. Determine the value of the following definite integral. So we need to integrate this. Let's put a little equal sign here. Alright, so it's a polynomial. So we're just increasing the power by 1. So that's going to give us x to the 4. And dividing by the new power. Well, I'm going to do multiplying by a quarter, which is the same thing. And then increase the power of this by 1. So we get x squared. And then we're dividing by the new power. So we've got 4 divided by 2, which is just 2. You could write that, but this is a multiple choice question. I'm moving relatively quickly. Alright, so I'm going to integrate that between 2 and 0. So now I just need to sub 2 into there, and then minus and sub 0 into there. Alright, so something like that. Now, what have we got? 1/4. 2 to the 4. A lot of people are going to say that's 8. 2, 4, 8, 16. All right. 1/4 of 16. That's 4. Plus 2 squared is 4. 4 times 2 is 8. All right. That's 12. Minus, and very, very often when you're integrating between 2 and 0, the second half here is just going to be a big fat 0, right? 0 to the 4 is 0, so that's 0. 0 squared is 0, so that's 0. Careful though. Just because you're integrating between 2 and 0 does not mean that's always going to be 0. If you've got trig functions and things like that, that's not going to be the case. All right, my final answer is 12. Perfect. Celebrate. Something I will mention about this question is that originally the question didn't look like this. Originally the question was written a little bit more like this, with all this like units squared here. And I nearly made the video with the units squared there, but we don't need them, right? Because we're not told that we're finding an area, we're finding a definite integral. Now, is the definite integral the area under the curve? Yes, it is, but if you're just doing a mathematical operation, you don't need this units squared thing here. Tiny little thing. Next question. All right, here we go. Have a try yourself. I'm going to do it. Tech free, no calculator. I really wish we had a calculator for this, but we don't. Don't forget, very good idea to draw a picture for questions like this. So what have we got? We've got a function, right? Well, what's it look like? I don't know, but it's a function. Okay, great. We want to find turning points in the domain 0 to 2 pi. So we're only going from here to here. And it looks like there's only going to be 2 turning points. So maybe I'll just redraw my function. Something like that, because it's got 2 turning points. Now, does it look like that? No, I've got no idea what this function looks like that. Why did I draw a picture? Because my brain is tiny, and if I have to picture things in my head, I haven't got space for other stuff. So I draw it, I outboard all my energy onto there, so then I can start thinking about other stuff. All right, select the coordinates of the turning points. You should be thinking turning points. That's when the derivative equals 0. So I should find the derivative of this function. So if y equals e to the sine x, then dy dx equals, we bring the derivative of the thing on the top of the e out the front. So the derivative of sine x is cos x. And then this part remains unchanged. So cos x times e to the sine x. And we need to find turning points, and that's when the derivative is equal to 0. So that means that 0 equals cos x times e to the sine x. So I'm going to put some brackets around this e to the x because I really want you to see something here. This is an application of the null factor law. You're used to the null factor law for questions like this, like x minus 2, x plus 3 equals 0, and finding that x equals 2 and x minus 3. But these don't have to be like linear terms. They can be trig functions or exponential functions, and the rule still holds. If something times something equals 0, then this must equal 0, or this must equal 0. So using the null factor law, 0 equals cos x, or 0 equals e to the sine x. Look at this one. E to the something equals 0. There is literally nothing that something can be raised to the power of to make it equal 0. So no solution there. That's not going to work. So then the question becomes, okay, when does cos x equals 0? And you should be able to like deal with your unit circle here, and you should be able to say that, oh wait, I know this. It's here and it's here. So then x equals pi on 2 or 3 pi on 2. All right, so that narrows it down. It's B or D, because these are the x coordinates where the turning points are happening. So this is like pi on 2, and this is 3 pi on 2. But now I need my y coordinates, and I can find that by subbing it back into the original equation. So let's sub pi on 2 in. Y equals e sine pi on 2. Okay, the value of sine pi on 2, again, you should know the value of sine pi on 2 is 1. So y equals e to the 1, which is e. So y equals e. Now that was at this point right here, pi on 2. So pi on 2, e. All right, that really narrows it down now. That point, pi on 2e, in this part here, there is only one point that I can see that has pi on 2e, and that is b. Now, we can go further here. If it was like a short response question, you'd then have to sub 3 pi on 2 into here to get e to the negative 1. And e to the negative 1 is equal to 1 on e. And you can see that's our other solution to B. All right, that's a good question. I like that. Celebrate. And next question. Short response, have a try at this one. A little bit of grunt work. All right, let's get started. Part A, that looks easy. Part A, we have e to the 2x equals 7. You should be very comfortable rearranging this into logarithmic form. This is the base, so it's log base e, otherwise just known as ln. But I'm going to write log base e because I want you to see what it is. Log with a base of e. Sometimes this sort of doesn't tell you that that's what it is. All right, and then we take this number, 7, and that's equal to whatever the power of that was in the beginning, 2x. Log base e7 equals 2x. That means that x equals, we divide the whole thing by 2, or, my preference, I'm going to multiply it by a half. Same deal. Log base e 7. And you know, in solutions, it would probably look more like x 1/2 ln 7, just because that's sort of mathematically efficient. But these are identical. These are the same thing. All right, that's part A. We've gone from exponential form to logarithmic form and then done an extra step, solved it. Celebrate, and we will do part B. All right, so part B, testing your log laws out here. So what have we got? Same basis, log base 4, and then we've got this plus in here. So you should understand that if you've got the same logs and you've got a plus, that can be pushed together into a single log. Log base 4, and then it's x times x minus 12. So this times this equals 3. Okay, what will I do next? Well, I guess I could expand this, but I'm not going to expand it. I think instead, I don't know what I should do, but I feel like maybe if I write this in exponential form, maybe it'll start to reveal itself. Don't be scared to try something and then just see what happens. So 4 to the 3 equals this, x times x minus 12. 4 to the 3, that's 4 times 4 times 4. That's 64. And then I think I am going to expand this now, because it's feeling a bit quadratic. All right, x squared minus 12x. If I'm going to solve this, probably need to be equal to 0. X squared minus 12x minus 64. Wow, okay. What is that? I was going to factorize this off camera, but I think maybe I should show you how I would do it. Okay, so I need two numbers that when multiplied together make negative 64, right? This value here. And I need two numbers that when added together make negative 12. Okay, so the way that I approach this is I try to be a bit systematic with it. I go, okay, times, would this be useful? 1 and 64, because they times together make 64. I'm not interested in the negative yet. No, that's not going to be useful. What about 2 and 32? That's not going to get me close to 12. Closer though. What about like 4 and 16? Ah, there we go. That'll work. All right, 4 and 16. 4 and 16. Now, I want it to be negative 12, so that means the 16's got to be negative. Great, great. I can factorize this now as x plus 4, x minus 16. The method I'm using here, there's lots of different methods for doing this factorization. In the comments, tell me what method you use. If this didn't make any sense to you at all, you might complete the square, you might use the quadratic formula. In any case, the answers I have are x, therefore x equals negative 4 or x equals 16. That null factor law came up again from the previous question. Now, it is going to be very tempting to stop here and celebrate because you think you've got two answers and we're finished. But when it comes to solving log equations, you've always got to think about things at the end. So we've got to do a check. We have to do a check. Every time we solve a log equation like this, we've got to do a check to make sure our two answers make sense. All right, look at this x equals -4, right? If I put that in here, I'll get log base 4 -4 in my beginning. That's a problem. You can't find the log of a negative. This is tech free, but I just wanted to show you, like, this is broken. It doesn't work. So x equals -4, we're going to reject that. All right, so we're rejecting x equals -4. The question is, should we reject x equals 16? Maybe there's no solutions to this thing. Maybe it just doesn't work. Well, let's see. Log base 4 16 plus log base 4 16 minus 12 equals 3. All right, so in this case, log base 4 16, that's fine. And not only is it fine, but I can figure that out too. And log base 4 16 minus 2 is 4. Log base 4 4, that's fine. Not only is it fine, I can figure it out. 2 plus 1 equals 3. Great. 16 works. The only answer is 16. Now, do not get the misunderstanding that, oh, we reject negative answers, we allow positive answers. If this question were different, it might be that the negative answer is the correct one and the positive answer is the one we reject. So you can't just look at them and say, that one's negative, that one's positive, keep the positive one, reject the negative one. You have to put it back into the equation because 50% of the time, the negative answer is the correct answer. Okay, x equals 16, I can celebrate, but there is a part C. Part C, pause the video, have a look at it. All right, I'm going to do it. Interesting question, right? We've got a base of our log that is a full linear equation, not just a number. So that's interesting. Now, there are, I think, probably 10 different ways that a person might go about solving this. I'm going to solve it in the way that just sort of feels natural to me. All right, I've got this negative out the front, so I could multiply both sides by -1. So that's going to give me -5 here. And that's going to give me log base 3x minus 1, 1 over 32. All right, I've got this all now. I feel like I should just write it in exponential form, right? So that means that 3x minus 1 to the power of -5 needs to be equal to 1 over 32. Okay. It's being raised to a negative power, right? So that means that if you're raising something to a negative power, that means it's being raised to the power to a positive power, but on the bottom of a fraction. So I could write this left-hand side as 1 over 3x minus 1 to the power of 5. And that's 1 over 32. All right, I've got 1 over this is equal to 1 over this, which means that this must equal this, right? So that means that 3x minus 1 to the power of 5 must be equal to 32. Hopefully you are looking at this and you're saying, oh wait, 32 power of 5, that's clever. 2, 4, 8, 16, 32. 2 to the power of 5, 3x minus 1 to the power of 5. All right, so if 3x minus 1 to the power of 5 equals 2 to the 5, then 3x minus 1 must equal 2. And from there, I think we should all be able to do that. 3x equals 3 and x equals 1. It's always cute when the answer is x equals 1. Like I said, there's probably 10,000 different ways to solve this. You might, for instance, instead of taking this negative in the very first step and dividing both sides or multiplying both sides by -1, you could bring the -1 way over here as a power of -1. And that would give you 1 over 32 to the -1, which would be 32. Right? That's cool. Well, that's a cool idea. But not the way that I went with it. This is good. Don't break any rules and you're fine. Let's celebrate. And we've got one more question. All right, we have an area between two curves. Have a try, then I'm going to do it. All right, I'm going to do it, and it's not going to surprise you here that my first step is to draw a picture. All right, so I've got a function, e to the x. Now that looks something like this. And then I've got this weird other function, 6 minus 9 e to the negative x. I don't know what that looks like. I could probably sketch it, right? Like, I feel like I could sketch it, but I'm not keen to sketch it, so I'm not going to at the moment. I'm just guessing that it must connect with this somehow, right? It must. And I'm just going to draw something, just random, that connects with that. So, I don't know, like that. It's definitely not that. But that's okay. Just draw a picture and keep going. All right, so we're finding the area between x equals 0 and its intersection point. We're finding that area. I'll update my picture as more information comes to light. Okay, I need to find the intersection point. That's important, all right? Because I can't integrate these two unless I know what that intersection point is. If you've got two functions and you want to know their intersection point, the easiest way to do that is just to make them equal to each other. E to the x equals 6 minus 9 e to the negative x. Oh, okay. This is not pretty, and it's not intuitive what you should do next. But once you've seen it once, you should spot the pattern and you should know. This is e to the x, this is 6, and this, I guess we could rewrite it as e to the x equals 6 minus 9 times, or 9 over e to the x. Talked about that in the last question. Negative powers, they come down to the bottom. Okay, once you've seen it once, you need to be able to do it forevermore. The trick with questions like this is to multiply every single term by e to the x. What happens when you do that? You get e to the x times e to the x as our first term. Now, e to the x times e to the x is e to the 2x. So that's that one. This one here, multiplying by e to the x, we get 6e to the x. And then this one here, negative 9 over e to the x times e to the x, we just get negative 9. And then you might still be looking at going, that didn't make my life better. But this is actually a quadratic in disguise. And I'll show you how you can see it's a quadratic in disguise. If we let e to the x equal u, then we can write this as u squared equals 6u minus 9. And given it's a quadratic, it's going to be easier if we set it all equal to 0. So we can say that u squared minus 6u plus 9 equals 0. Okay, that rings a bell, right? I think I can factorize that as u minus 3 squared. All right, so that means that u minus 3 squared equals 0. Which means that u minus 3 equals 0, if I just square root both sides, which means that u equals 3. I don't want to know what u is, I want to know what x is. Remember that u is e to the x, right? So, we can say e to the x equals 3, and we can write that in logarithmic form, log base e3, so ln 3 equals x. Oh, wow. Okay, what did I just find? I found the intersection point of those. The intersection point of these is ln3. In the tech-free exams, you're going to end up in situations where you have to deal with values like this. Not just the number 2 or 5 or 3.7, but ln something, e to the something. Where they don't neatly turn into numbers. You've got to hold them like that. Okay, so I've updated my picture slightly, but I think I still have a small problem that I have to deal with that. Let's get rid of this, make some space, and move on to step 2. Now, if I want to find the area between two curves, it's pretty straightforward. I'm integrating between the starting point, 0, the ending point, ln3, and then I'm doing the top function, which whatever that is, minus the bottom function, whatever that is, all with respect to x. The problem I've got at the moment is I don't know what the top function is. If you remember, I said e to the x looks like this, and you should all know what e to the x looks like. It passes through the y-axis at y equals 1 and goes up like that. But I don't know what 6 minus 9e to the negative x is. I could do a bunch of function transformation to figure it out, but instead, I don't need to know exactly what it looks like. I just need to know whether it's above or below e to the x. And so the way that I'm going to do that is to find the y-intercept of the function 6 minus 9e to the negative x. Finding y-intercepts is easy. You just let x equal 0. So if I let x equal 0, I get 6 minus 9e to the 0. Now e to the 0 is 1, so 6 minus 9 times 1 is 6 minus 9, which is negative 3. What does all this mean? It means that this g of x function, this minus, has a y-intercept not up here, has a y-intercept all the way down there at negative 3. That means that my drawing needs updating, right? My actual 6 minus 9e to the negative x function is not there. It must be something a bit more. I don't know what it looks like still. All I know is it passes through here and it meets there. That'll do. That's the actual area I'm looking for. So the function that's at the top is e to the x, which means I do e to the x first. I don't do it second. So I rewrite this, ln3, 0, and then we're doing e to the x minus, and then we've got to be careful here with our minuses with respect to x. Okay, what can I do with that? I've done these brackets here, right? I'll just rewrite it one more time. ln3, 0, e to the x minus 6 plus minus plus 9e to the negative x with respect to x. Okay, what is the integral of this? Because I'm going to be integrating between ln3 and 0. Integral of e to the x is e to the x. The integral of negative 6 is negative 6x. And the integral of 9e to the negative x, we bring that negative out the front because we need the derivative of that to come out the front. So positive 9 times negative 1 is negative 9e to the negative x. So there's my integral of that. And now I sub in ln3 into this, and I sub in 0 into this. So it gets pretty wild here. We're subbing in ln3 for x, subbing in ln3, subbing in ln3, subbing in 0, 0, and 0. All right. Let's deal with this first, because this is interesting, because in a previous question I said, hey, be careful with when you're integrating between something and 0, because this isn't always equal to 0. What is it equal to? Well, e to the 0, anything to the power of 0 is 1. Now, 6 times 0 is in fact 0. Now this, negative 9 times e to the 0. E to the 0 is 1, so negative 9 times 1 is negative 9. All right, so minus 1 minus 9. All right, that's that bit done. Something you should just be able to spot like that is e to the ln3. That e and that ln cancel each other out. You can watch last year's one where I went through a question where I explained everything about why they cancel each other out. But for this video, we're going to assume we know why they cancel each other out. E to the ln3 equals 3. All right, minus 6 ln3. Not much I can do with that. And the last one I've written out for you already, negative 9 over e to the ln3, right? Because we've got a negative power there, which brings that e down. And we've already established that e to the ln3 equals 3. All right, so what does all this come together to be? 3, let's deal with all the numbers, right? This is 1 minus 9 is negative 8. So minus 8, that bit here is a positive 8. So I'm just going to write that way up here, positive 8. This bit here, 3 minus 3. They cancel each other out. And so then all I'm left with here is a negative 6 ln 3. Negative 6 ln 3. That area, that one right there, is equal to negative 6 ln 3 plus 8. Probably more polite to write it in that order. A lot of steps there, but nothing we can't handle. We found the intersection point, and then we found the area between two curves. And remember, we were just drawing just a couple of pictures. All right, let's celebrate. That question is done. All right, that's it. That's been part 3 of Guessing the Methods exam. As usual, thanks to my peeps here. They've written the exam, and it is like fantastic. I'm loving it. Go and check out the tutoring company. Maybe you could be a tutor yourself. Maybe you can get some tutoring, sign up to the newsletter, etc., etc. Link in the description. See you in the next one.